Hello, for today's our topic is full adder. So in case of full adder, we have three inputs. Out of three, two are the significant bits, and one is the carry, which we are getting the addition of the two significant bits. And we'll have two outputs. One is the sum, another is the carry. So in the to design the combinational circuit, first we have to decide how many inputs, how many outputs are there. Later we have to write the truth table. So once we'll get the truth table, from that we have to get the Boolean function. And finally that Boolean function is being implemented by using the logic gates. So in case of sum, already we have seen that when we have 1 plus 1, sum is 0, carries 1. This situation is only new for you. Otherwise, remaining 0 plus 1, 1, 1 plus 0 is 1, 0 plus 0 is 0. That carry is always 0. So now here, first, we are going to add x plus y. So that is going to give us 0 plus 0, 0. Again, this 0 is being added with z, that is the 0. So finally, sum is also 0, carry is also 0. In the second scenario, again, x plus y, 0 plus 0. Again, this outcome of this is sum is 0 is being added with this 1. So 0 plus 1, sum is 1, carry is 0. Again here 0 plus 1, sum is 1, carry is 0. So now this 1 is being added here with this 0. So 1 plus 0 is 1, carry is already 0. Now in this situation 0 plus 1, 0 plus 1 is what? 1 here. And finally this 1 is being added with this one. So 1 plus 1. Now sum is 0, carry is 1. Now in the another combinations, when we have 1 plus 0, sum is 1. Now this 1 is added with this 0, so sum is 1 and carry is 0. Now 1 plus 0, sum is 1, carry is 0 here. Now this 1 is being added with this one. So 1 plus 1, sum is 0, carry is 1. Again here we have 1 plus 1, sum is 0 here and carry is 1. Now this 0 is being added with z, that is the previous carry we consider. So 0 plus 0, sum is 0. Again we have 1 plus 1, sum is 0, carry is 1. So now this 0 is being added with this one. So 0 plus 1, we have 1. Like this we are able to complete our truth table. Now from this truth table, we have to obtain the Boolean function. So for that purpose, we are using the K-map. Now this first one, this is taking for the sum. So here we have three inputs. So to the power 3 is the 8. So 8 square boxes are required in the K-map. So whenever we have sum as the 1, for that we are going to write the mean term. So here sum is 1. So that combination is what we have 0, 0, 1. So that mean term is 1 here. Second, again we have 1 here. For that 0, 1, 0. So 0, 1, 0, that equivalent is how much? 2. So that we'll write here 1. Again we have next here 1, 0, 0, that is the 4. So we are writing 1 here. This is the 1, 1, 1, that is the 7. So mean term here, this is the 1. Now if you see that in this, any combination is not possible. We are not able to make either pair or quad, anything. So all are isolated one. So for this, we can write the expression for the sum. So that sum will be equal to here. Now suppose we'll write for first mean term here. So that we have to write x dash y dash z plus, again we'll write for this mean term. So row wise you have x dash, column wise we have y, z dash plus, now we'll write for this one. So here row wise we have x, column wise y dash, z dash plus, for the last one, row wise is same x, and column wise we have yz. So this sum again we can simplify here and we can write in the term of XOR gate so that further it will be easy for us to simplify. Like from here, if you see that we can have simplification in this part. So for the first two terms, what is the common? X dash is common. For the second term, what is the common? X is common. So now further, this one we can write as sum equal to x dash is common. So finally we have y dash z plus yz dash plus again here x from last two term. We have y dash z dash plus yz. So if you see that this is the XOR gate and this combination is the XNOR gate. So finally this one we can write as x dash y XOR z plus x into y XNOR z. So now again here x dash, suppose for example this one you will consider some new variable, suppose for example for short time. So here suppose we'll consider this one is the m. So this one will be going to become for us m dash. So finally again x dash m plus xm dash. So again it is what? XOR gate. So finally you'll get here x XOR m. So this can be written as now x XOR y XOR z. So here we have two XOR gate for the sum. Similarly, we can see for the carry. So for the carry again, K map is required here. So for that carry, now again, if we are now we are going to see this column where we have C. So whenever we have 1, so that 0, 1, 1, that is equivalent mean term is what? 3. So here we'll write the 1. Again, you have 1 here, so 1, 0, 1. So 1, 0, 1 is the 5. So we'll write here 1. Again, we have 1, so this is the 1, 1, 0, that is the 6. So we'll write 1 here. Last one again 1. So we have triple 1, that is equivalent to 7. So now here we are able to make the at least pair we are able to make. 3 pairs we can make here. So one combination is this one. So for that, if you see that what is the row wise column, row wise is the common is the x, and here we have column wise, that is the common is the y. So this is the xy for this. Similarly, we can have another combination also. So in that again this pair. So for this pair again, combination row wise what we have x. Column wise what is the common here? 1. So again this one we are writing x, z. And last one more pair is there. That is the mean term of 2 and 7. So for this again, row wise nothing is common. Column wise what is the common? Yz. So finally here for the carry, we are going to get the expression xy plus yz plus xz. Now this also we can simplify further so that it will look in the simplest way. So that it will be easy for us to implement. We can minimize the number of AND gates here. So now for that we know that we have concept of so if you see that in this case this xy is same as the what we have in case of half adder. So now this full adder we can see as the combination of two half adder. So on the that line we are trying to arrange these terms here. So this initially this xy will keep as it is since xy is already there in the previous situation also. So now remaining yz and xz we are going to make the change where each term will have all literals. So for that you know that if you have a plus a dash, that value is 1. So like this complement and plus that number will multiply here. So that value is 1, so not going to make any change. So on the basis of that here we have xy plus yz, so which is literally is not here x. So we have x plus x dash we can multiply. Similarly, in the third term, which is missing, y is not there, so we can write y plus y dash. Now again, if you will expand this one, if some term is common, so that term will write only one time. So finally you have xy, again here xyz plus x dash yz plus again xyz plus xy dash z. So here this xyz is coming two times. So we are going to write only one time about this. Okay. So finally, whatever mean terms are there in that, what are the common? So here we can write x plus xyz plus x dash yz plus xyz, y dash z. So this xyz we have written only one time. Now see that what is the common, what anything we are able to get the common, so that will take. So in the last two term, if you see that we have z is common. So this one will write xy plus xyz, and here z is common, so x dash y plus xy dash. So this is coming as the XOR gate. Okay. So again here in the first two term, what is the common? Xy is common. So xy will take common, so 1 plus z. So 1 plus z, you know that it is the OR gate. So OR gate, if any one input is high, output will be high only. So this one will write as it is. So from here, what you are getting that this term, from first term, we have xy only, plus here we have z, and this one we can write x or y. So this is the how we are able to simplify the sum and carry, so that we can implement this one also with the help of two half adder. Next, we are going to see how to draw the logic diagram from the obtained Boolean function, so that we can see quickly about this. So this is the function that already we have obtained. From that, we have to draw the logic diagram. So in this here we'll have one XOR gate. Again, another XOR gate is there. So this circuit is going to look like this. So first we have one XOR gate. So this XOR gate, what is the input here? For this, one input is X, another input is what? Y here. So finally output is here X XOR Y. And further, this output is going to be again XOR with Z. Okay. So again, we have to give the Z here as the another input. So total 3 inputs we have. So we are connecting the Z to the second XOR gate. So this one is literally Z. So finally here we are going to get X XOR Y XOR Z. So this is the expression for our sum. So now sum we have represented. Now we have to represent what? Carry. So for the carry again, if you see that the first term is what? XY. So for that, one AND gate is required. So input is here same X, and another input is what? Y. So if you see that this first stage is looking same as half adder. So this output is here XY. Now again, here if you see that we have XY XOR, that is going to be AND with Z. So again, one more AND gate is required here. So this AND gate, one input is what? That is the X XOR Y. Another input is what? That is the Z. So that Z should be connected here. So finally, here we are going to get what? This is the Z into that is X XOR Y. Since here input is what? This is the X XOR Y, and this one is the Z. Now finally, you are seeing that this XY is sum with second term. So here what we required? One OR gate is required. So finally, one OR gate we are going to use for this purpose, so that it will add these two values. So we required one OR gate that will give the carry. So this is the one of the input. Another input we are going to take from here. So that is the XY. So this one is the carry. So this input is here XY. So finally this carry expression is what? XY plus Z into X or Y. Like this, we are able to implement here. And this part is what? It will look like if you see that half adder. So this is the combination of one half adder. So this one is our half adder one. And again, if you look for the another part, this part again, you'll have, this is the half adder two. So like this, we can represent the full adder with the help of two half adder also. So these are the discussion. So here, if you see that in this portion, we can keep line up to this portion only, since we have only two input is required for the half adder. So this line will come up to this portion only. So in case of full adder, we have three inputs, whereas two inputs are the significant bits, and third one is the carry, what we are getting the addition of the previous two bits. Thank you. Thank you.